So let's continue. In the previous video, we extracted features from different conv layers and we saved it in a pickle file. Now we'll use these features to train a logistic regression. Now, one thing to note here is that in case of the first feature, say feature 1, extracted from the layer 4, the dimension of features is 8192, and since there are 400 samples, it's for each sample there are 8192 features. And for the second type of features, which was extracted from layer 3, the number of dimension of each features is 16,384, and in case of the third case, it's 32,768. Now, if you see the number of samples, it's not that much. So there could be, the curse of dimensionality because of, huge number of dimension in the features. Maybe the network does not train well, learn well. It also overfits, and also one thing we can do is, we can simply train with whatever input features we have. We can simply train a logistic regression, and you can use whatever technique you use to improve on your logistic regression. And also we can reduce the dimension of this. So one option is simply you have these features and then train it, and other is we could reduce the dimension of the features. And I think you might be aware of the popular techniques to reduce the features, like the PCA, autoencoder, or kernel PCA. And so we'll take these features, we'll pass through these techniques, and we'll reduce the dimension of features. It could be any, and then I will show you how you can do that with the scikit-learn, and then you can train a logistic regression on it. So let's go to the code. So this is my code, and before we train the logistic regression, I would like to explain this PCA dimensionality reduction approach with the scikit-learn. So we have the features, so we'll load one of the features, say features 1, and then we'll simply, this is just to check, and we'll read it. So let me just call it one by one. This is just to check, and here's the output. So I'll use a pickle.load to load the train features and the test features along with the labels. And then what I'm doing is simply, getting the train and the labels and converting them into an array. Okay. So if you see this, the train shape would be 400 samples, and for each samples the dimension is 8192. Now let's see how we can reduce this dimension. Okay, so we have to simply call this PCA class, which we imported from the scikit-learn, and then you have to do a fit transform to this X training or TR. And once we do that, it's done. So we can have this function called explained variance, and if you print this explained variance, then it will show the variance of each dimension. However, there are a lot of dimensions. So what I did, so suppose if you see, you want to just observe that how much variance is covered in the first 30 dimension. So if you run this explain variance 0 to 30, it says that the first 30 dimension, they cover around 71% of the variations. So I just checked for around 300, and it was covering around 98% of the variance. So we don't need the full 8192. Maybe we can train with just 300. So this is one thing that you can try out. Again, depends. You can use many techniques, different optimizers. So just use how you optimize your logistic regression. So this is one point that I wanted to discuss, and I've included this as a function in this linear eval. I've included it as a function called as get PCA features. So we can get this PCA stuff. And in order to train this, we have this script called linear eval.py, which is in the SSL eval, and this PCA dimension reduction is also in this folder. Now let's see the configuration before we go into the training of this script of linear eval, which will be training with all the 3 different kind of features. So let's open this. So you can see number of classes, it's 5, and this normalize is actually normalizing the features, and here I am using I'm using this scikit-learn standard scaler to normalize it. Okay, it's just straightforward from there. And then this is simply defining the root path, then the dataset path. I think this is not needed here, but yeah, experiment type, just to say that it is in the self-supervised. And then what will be the saving directory? I'll name it as linear experiment 1 images directory, which we don't need here because we have simply will be using the pickle file from here, and the log file, and then feature extract experiment directory, it is the SSL RotationNet. So whatever experiment you did with the self-supervised and whichever features you want to use it, and then which you want to train from which of the features 1 or features 2 or features 3, so you can just mention it here. Then PCA dimension, if you put PCA dimension as false, then it will be using the dimension as mentioned, as saved in this pickle files. But if you give a dimension, say 300 or 400, then it will reduce the features dimension to that before training. And this is the learning rate, momentum, scheduler, the optimizer, epochs, batch size, and we don't think we're using mean now. And then image, this we don't need for this. Then validation split, and then CUDA if you want to use the CUDA. So this is our configuration file. So in order to run into this, you have to just change this one, linear experiment 1 for the first experiment, and then for that experiment which features you want to try out. So now let's go to the script. So I will just name as linear experiment 1, and the features first I will do with features 1. Okay, and then I will go to linear eval script. Now if you go to the main function first, so basically I am just loading this config file, and then after that I am simply defining where my feature directory is. It's in the root path, experiments, experiment type is self-supervised, then feature extraction has the feature extracted are saved in SSL RotationNet, and then which features, it's features 1. So it will simply set path to here, and then what I'm doing is I'm getting the data. So this get data function, if you see what it does, it simply loads the pickle file, and then it will load the arrays, the features and the labels, and then it will convert into array format. And if we are using this PCA dimension, then it will reduce the dimension to whatever dimension you define, as we just saw. And then I am doing a validation split from the train data, like 15% of the train data I'm using as a validation because I don't have an explicit validation set here. And then I'm simply deleting these dictionaries. And then I'm loading the labels. Oh, sorry, this was for the train, the data and the labels. And then for the test as well, I'm doing the data and the labels. And then, yeah, I'm simply, it returns the red train array, and then the train labels, then validation array, validation labels, and test array and test labels. Okay, cool. And then once we have the data set, then we're simply defining the experiment directory. For us, it was linear experiment 1. It will be saved here somewhere, outside, inside this SSL RotationNet because it's a part of it, and outside it. And then we simply create the directory if it's not there, and then we start logging, and this is to set the device. It could be CUDA, any number, or CPU, and this is again defining the writer function. So I will be saving all the say for this linear experiment 1 for all the features, feature 1, feature 2, feature 3, whatever experiment I'll do, I'll be saving it in a folder called TensorBoard linear. So first experiment will do without PCA, and then it will be saved as linear probe feature 1, linear probe feature 2, feature 3. So we'll see it. And then I'm defining the model. So we have defined a class here called logistic regression, which simply is a linear layer taking the input as number of features and output as number of classes. That's all. Simple logistic regression. Okay. And then I have this train and evaluate, the same way we did for our CNN training. So train and evaluate, it will define the optimizer, scheduler, then it will for the number of epochs defined, it will do a training, get the train loss, train accuracy, it will do the validation, and then it will save the checkpoints depending on the minimum validation loss. And then at the end, whatever the best checkpoint is there, it will load that checkpoint and evaluate on the test data. And then we'll close the writer, and then we'll save the config file and then close it. That's all. So let's do our first experiment. So this all I think I have discussed, while the CNN training, it's basically the same thing, defining a loss and accuracy object, and then defining the model.train, and then looping over every batch, and then simply training it. Okay, fine. So what I'll do, I'll go to this config I have set here, and then I will save this. Okay, and then I will run this script here. Okay, so it should be here in eval, ssl eval, and then python linear eval.py, and then let's see, it will start training. So yeah, there were 400 samples, of which 400 training samples, of which 72 has been taken as validation. So it'll be very quick because the number of samples is less, and it's just a logistic regression. But yeah, the result won't be good. I just did initial parameter setting. I did not optimize it further, but you can try out. You can use whatever logics that we use for logistic regression. So meanwhile this experiment is being trained, what I'll do is I'll set it for the next experiment. So I'll just simply make it features 2, and that's all. Okay, then it will take this features 2 and train on this. Okay, nothing else that I have to do. It's everything defined here in this. So let's see if this training is complete. A bit, and yeah, it's complete, and we'll see here that there's linear experiment 1 and the training results and checkpoints of features 1. Now we'll do for the features 2. Okay, so one thing is yeah, let's do for features 2. I think it should work. So it will start the training. And so I think this was without PCA, right? Oh yeah, PCA dimension is false. So okay, and let's set it for the next experiment. Simply make it features 3 and control save it. Okay, it's done. So let's train for features 3, and now we'll also train, before we see the results, let's also train an experiment with the PCA dimension. So what I'll do is I will name it as a new experiment, and then I will again do it for all the 3 features. So start features 1, and then I'll set PCA dimension as 300 for now. So for each of the features, features 1 to 3, you can then just do some experiment just to see, what is the how much number of features are covering the variance, and then you can change it here. So for me, I think in this case 300 was covering. Okay, so I'll just make it 300, and let's hope that this got trained. Yeah, and if you see here, so we have linear experiment 1, the training results for all the features, and then a tensor board to see the results. So we'll go to the tensor board, but let's also finish training this PCA with the PCA dimension reduction. Okay, so with the features 1, let me train it, and then we'll start training, and then I will make it ready for next training just by making it features 2. That's all we need, and saving it. So let's see if it gets trained. It got trained already. Okay, almost done. Okay, great. Now I think let's do for features 2, and then while it starts, I'll make it ready for next features 3, and then I'll also try to load a tensor board here. So just to show you the result, so I'll activate my environment, and it was D, and then self-supervised learning, PyTorch, and then it was under experiments, and then self-supervised learning, and then RotationNet, Yeah, let's see. Yeah, so okay, let's hope that I trained for 3. Let's see. So linear experiment 2, features 1, 2. Okay, now we'll do the last training. Meanwhile, let me open the tensor board for the first experiment of linear experiment 1 without the RotationNet. So I'll have tensor board log directory as tensor board. Okay, I need to change it to linear experiment 1 and then tensor board log directory was tboard linear, and then I'll open it on the port 6008. And I think the okay, is the training not done yet? Okay, it's complete. Okay, did I not change it? Oh, I forgot to save it. Okay, I did a mistake here. So okay, let me just save it. Meanwhile, we'll see the tensor board, no worries. So yeah, so let me open it here. Chrome. Yeah, so let's see. And then I'll make it 3, save it, and then okay. Okay, so you see these are the training results, and then if you remember, linear pro features 1 was with the 4th layer. If I can go back here, this is with the features extracted from this one, and then the features 2 is this one, and features 3 is this one. So let's see which one is doing the okay. So it's clearly overfitting. The training is good, but the validation is it's not good. But if you see, so starting with the linear pro features 3, the accuracy is high. Then linear pro feature 2, it's a bit low, and then linear feature 3 is feature 1 is close to this. So again, it's not optimized, as I said, and also using RotationNet features for the flower dataset also it's a bit tricky, so we need to optimize it. But I just wanted to show you how the experiment setup is, and you can obviously try it and try to optimize it further. But again, for the 3, even in the when we were trying to use the conv features, the features extracted from this, conv layer 2 was working the best. And as also, we can see it here in case of the validation accuracy here. Now let's also see what happened if we used a PCA dimension and see whether it improved or not. And one more thing is, let's see the test accuracy. We didn't saw the test accuracy. Yeah, so for the linear probe feature 1, it's 37%. Features 2 is 33, and for features 3 it is 34. Okay, so it's I think in case of test performance, this one is working the best, the pro feature 1, which is this one. But again, I think this need to be further optimized. So right now it's not optimized. It need to be further optimized and all. Okay, now let's also see with the PCA the experiment, linear experiment 2, what's happening there. So I'll open another console, and I will save this part here, and I will have my PyTorch, and then experiment 2, and then tensor board. Okay, I did not change the name, but okay. Port equal to 6009. Let's see. Take some time. Okay, so yeah, so but as I said, okay, these results are not great. Obviously, it's seems very bad. But one thing, as we discussed, the RotationNet, you know, has challenges when with the data set where there are no salient features with respect to the orientation, and also this logistic regression parameters that I have defined, it need to be changed, and see, maybe we have to try with different learning rate, change Adam optimizer and try it, and change the batch size and all, and then see which, how it performs. Let's meanwhile see if that got started. Oh, not yet. Okay, it was stuck somewhere. But I know it will start on 6009, so I can simply do a local host 6009. Let's see. Okay. Okay. I think I should have deleted the previous experiment, because for the features 2, it combined both features 2 and 3. But nonetheless, here also we can see, I should have deleted it and then retrained it, which I didn't. But nonetheless, we can see that, if you see the linear feature 3, it has the highest accuracy. Feature 2 got a little bad. Feature 1, it's better than the 2 close to 3. Okay. Again, kind of same performance even with the reduced dimension. But I think the validation, let's see the test results here. Okay, it's only for proof. Okay, yeah. So the test result, okay, it's bad. It's bad then, because we reduce the dimension of test features as well. It's bad then without reducing the dimension, but okay. And this was because in this features 2, we train features 2, features 3, and again feature 2, that's why 3. So I should have deleted it. But nonetheless, you got the idea of how we are doing this training, and the linear evaluation training. So you can simply play with this config file and this code. Once you've saved the features, just change the experiment and try out, and then see how it is. And also try it for different data set, because as I said, flowers data set are just for trial. Try it on your custom data set, and then let's see how it goes. So I hope yeah, I think this is all from now. So that is it from the RotationNet side. So there were a couple of videos where we discussed and implemented RotationNet. First of all, we discussed RotationNet, and then we implemented in a custom dataset, the flower dataset, and then we evaluated it using transfer learning and the linear evaluation. And we saw that the features extracted from the layer 2, they were giving the best result, although it can be further optimized to get a higher result, and also the linear evaluation part, you can further optimize it and to get a better performance. But nonetheless, the idea was to understand how it's implemented and how it's evaluated, and that we did in this couple of videos. And this also complies with the paper, that in their case also the features extracted after the second conv block was giving the best result, because because we are doing a training of predicting rotation. So if you take features from deeper layers, their features are more oriented toward predicting rotation and not a very generic feature. So it makes sense. And we also saw that this RotationNet might not be a good idea for dataset where there are no orientations or no orientation features which with respect to the entire image, as in case of this flower dataset or some texture dataset. But nonetheless, overall, I hope you learned something from it. And in the next video, we'll discuss a very interesting approach, which is kind of one of the state of the art, the SimCLR from Google, a simple framework for contrastive learning. And this is a very interesting idea of augmenting one image with two different augmentations, and then see if they're close to each, if they're coming from the same image to different augmentation, then try to bring it close, and if they're from separate image, then try to make them far. That's the logic. And in the next video we'll discuss this, and yeah, I hope we will learn something. So Till then, keep learning, be safe, and keep exploring neurons. Bye.